Welcome to the lecture on graphing exponential and logarithmic functions. Let's start off by graphing the function 2 to the x. If you don't have any idea what a graph is going to look like, then the first place to start is by making a table of values. So we're going to make a table of values, an xy table, and to get sufficient points, I'm going to pick a nice selection of x's, so maybe -2, -1, 0, 1, and 2. And all I'm going to do is take those x's and substitute them in for this x, where that exponent is. So this would be 2 to the -2. Now to figure out what that is, you want to remember that a negative exponent flips your number over, makes it become a reciprocal. So 2 to the -2 is really the same as 1 over 2 to the +2, and 2 squared in the bottom becomes 4. So this is going to give us 1/4. If I substitute in -1, then this becomes 2 to the -1. If I flip it over, it becomes 1 over 2 to the +1, and that just stays 1/2. If you plug in 0, what you want to remember is your law of exponents that says any base raised to 0 power becomes 1. If I plug in 1, 2 to the first stays 2, and if I plug in 2, 2 to the second becomes 4. So now we have some nice points we can plot. -2, 1/4, we're just going to approximate where that would be. It should be over here. -1, 1/2 is just going to be a little bit higher than that. 0, 1 is going to be right on that y-axis, and 1, 2 is going to be right there, and 2, 4 is going to be up here. Now, if you can imagine plugging in more and more of these values for x's, what's going to continue to happen? Well, as the x's get larger and bigger and more positive, then these powers of 2 are just going to get larger and larger, and this is going to grow upwards very, very quickly. In the opposite direction, as x gets more negative, the more negative we make the number, the smaller this denominator is going to be, so the smaller the fraction gets. Does it ever actually equal 0? No, we get really close to 0, but we never actually hit it. So this is what's called a horizontal asymptote. We get really, really close to that x-axis, but we never actually cross it. So this has a horizontal asymptote at y equals to 0. Okay? Let's try another example. This time the base is going to be 1/2 to the x. This is called an exponential function because the base is a constant and the variable is up in that exponent, up in that power. So let's make our table again, and I'm going to use the same x values that I used before, -2, -1, 0, 1, and 2. This time when I plug in a -2 into that exponent, because our base is already a fraction, when we go to flip, because of that negative exponent, we can just flip the fraction on the inside of these parentheses. So when I flip 1/2 over, it just turns into a 2, and now the exponent becomes a +2. So 1/2 to the -2 is the same as 2 to the +2, and we know that that's 4. So if we try that again, 1/2 to the -1, instead of flipping the entire fraction under a 1, let's just flip the fraction over on the inside of those parentheses. So 1/2 flips over to 2, and the exponent becomes positive, and 2 to the first is just 2. If I plug in 0, 1/2 to the 0, anything to the 0 is 1. If I plug in 1, 1/2 to the 1 stays 1/2. And if I plug in 2, 1/2 squared, you square the 1, which stays 1, and you square the 2, which becomes a 4. So we get -2, 4. We get -1, 2, 0, 1, 1/2, and 2, 1/4. So it has the same points that we had over here, but going in the opposite direction. So we're going to fall and decay just like this. And again, we get really close to that x-axis, but we never actually cross it. So this also has a horizontal asymptote at y equals to 0. So these are called exponential functions. Again, the base is a constant, and the variable is the power. And if you want to generalize these two types of graphs, we have this list of characteristics that every exponential graph is going to have. If you start with any exponential function with a base of b, so b to the x, every exponential function will contain 0, 1 if it's of this form. And that's because if I plug in 0 for that x, b to the 0 is always going to give me 1 back. So it always goes through 0, 1 on that y-axis. If the base is bigger than 1, like our very first example, then you get what's called exponential growth. The graph rises as you go left to right. If the base is a fraction, like our second example, then you get what's called exponential decay, and the graph falls from left to right. So a base bigger than 1 is called exponential growth and has this shape, and a base that's a fraction is going to give you exponential decay, and it has this shape. All of these exponential functions, b to the x, have a horizontal asymptote at y equals 0. The domain is minus infinity to positive infinity, and that's important because that means you can use any x that you want. The domain allows every value of x. However, looking at these two graphs, we can see that the range is only going to be 0 to infinity, and we never actually hit 0, so that's why there's an open parentheses around it. Another characteristic of our exponential function is that it is 1 to 1. It passes that horizontal line test, and that's important because if a function is 1 to 1, that means it has an inverse function, which in this case, the inverse of an exponential is going to be a logarithm, and we will get to those in a little while. Okay, so now what we're going to do, once we have these basics down for an exponential graph, is we're going to do transformations of them. So we're going to take our basic exponential function and we're going to shift it up, down, left, right, and maybe even flip it over. So, for example, if I have 2 to the x plus 1, you should recognize that this plus 1 on the end is going to be a vertical shift up 1 because it's away from your function, away from that x, off to the side, and if I see a plus 1, that means we're going to go up 1. So that's kind of what you want to predict to happen. If we go and we try to graph here what this is going to look like, we can make a table of values again. Instead of doing 5 values, -2, -1, 0, 1, and 2, like I did on the earlier examples, it's sufficient to just plot -1, 0, and 1, just 3 points, now that we kind of know what the shape of this graph should look like. So I only need to choose these 3 x values. If we plug in -1 into our function, this is going to be 2 to the -1 plus 1. First, we need to figure out what 2 to the -1 is, and remember that just flips over the 2 and makes it become a 1/2. So 1/2 plus 1 gives me 1.5. If we plug in 0, 2 to the 0 becomes a 1. 1 plus 1 gives me 2. And if I plug in 1, 2 to the first stays 2, plus that 1 on the end gives me 3. So now I have 3 points to plot. -1, 1.5, 0, 2, and 1, 3. And when I graph these, we're going to get that exponential growth shape because we have a base of 2, a number bigger than 1. And remember that horizontal asymptote. Normally a horizontal asymptote starts at 0, but remember we had a vertical shift up 1. So if we shift our entire graph up 1, that horizontal asymptote gets shifted up 1 as well. So a lot of times what I'll do is I will write down what my new horizontal asymptote is. So it's going to be y equals 1, the same value as our vertical shift, and on my graph, I will show that and designate it by graphing a little dashed horizontal line. And that just helps remind me not to cross that horizontal asymptote. So when I connect these dots, we want to do our growth going up and to the right, and then we want to just skim the surface of that horizontal asymptote. And you want to make sure that you do not cross it or go below it. And so here's our graph. Okay, let's try another example. We have 3 to the -x. So if we go to graph this, remember that it's going to be sufficient to graph any exponential function by using the three inputs -1, 0, and 1. So if I plug in a -1, I'm going to get 3 to the -1, which becomes 3 to the +1, which is just 3. If we plug in 0, 3 to the -0 stays 3 to the 0, and anything to the 0 is 1. If I plug in 1, I get 3 to the -1, and a negative exponent flips us over, so this just becomes 1/3. So the 3 points that I have to plot here are -1, 3, 0, 1, and 1, comma, 1/3. And if I keep in mind the horizontal asymptote, remember every horizontal asymptote occurs at y equals 0 if we do not shift vertically up or down. And this one does not have a vertical shift off to the side because there was no number added or subtracted. So this horizontal asymptote should stay at y equals 0. So if you want to sketch in that little dashed horizontal line, just to remind you, then this is going to be an exponential decay graph because it's rising up to the left and skimming this asymptote off to the right. Now you may say, well, how come this is decay? Because we had a base of 3 and that's bigger than 1. Well, remember what this little negative does. In terms of transformations, this negative, when it's next to that x, is a reflection. And this is a reflection over the y-axis when it's next to that x. So if you think of this as 3 to the -1 raised to the x, 3 to the -1 is the same as 1/3. So this 3 to the -x is actually the same as, should give us the same graph as 1/3 to the +x. And that's why this is an exponential decay, because it's acting just like a base of 1/3. Okay? Alright, on the next example, let's look at those transformations first. Here we have a minus on the outside, not up near that x like in the last example. So this minus is also a reflection, but this time it's a reflection over the x-axis. We have a base of 1/2, so this is going to start out as an exponential decay. And then we have this -2 on the end, and when it's off to the side like this, then that's going to be a vertical shift. And because it's a -2, we're going to go down 2. And right away, as soon as I recognize that there's a vertical shift, then I know right away that I'm going to have a new horizontal asymptote. Instead of being at y equals 0, we want to shift it down 2. So now it's going to be at y equals -2, the same number that you have on the side here. So let's go ahead and sketch in that horizontal dashed asymptote. So we want to make sure that we don't cross that. Now to get the rest of our graph, you can always plot points. So remember, it's always sufficient to use -1, 0, and 1 for your x values. And we're going to be plugging them into this function. So if I plug in a -1, then I want minus parentheses 1/2 to the -1 minus 2. Now a -1 exponent flips over this 1/2. So when you flip over a 1/2, it turns into a 2. But there was that minus in front, and there was the -2 on the side, so we end up with -2 minus 2, which is -4. Okay, so now let's plug in 0. If we plug in 0 for x, anything to the 0 turns into 1. And there was a minus in front of that, and a -2 on the side, so -1 minus 2 gives me -3. And finally, if I plug in 1, 1/2 to the 1 stays a 1/2. There's a minus in front of that, and that -2 on the side, so -1/2 minus 2 is going to be -2.5, or -2.5. So now we have our 3 points that we can plot, -1, -4, 0, -3, and 1, -2.5. And keeping in mind what this should look like, remember we have that horizontal asymptote. You can see that these points are kind of going upwards towards that asymptote, so we want to continue that pattern and skim the surface of the asymptote. In the opposite direction, they're going downwards like this. So we get that exponential decay graph, which would normally go like this, but it's been flipped upside down because of that reflection over the x-axis, and then we shifted that all down too. Okay? Alright, let's try another one. 3 to the x minus 1. This time, for our transformations, we have a minus 1 up there near the x. So this is not going to be a vertical shift, this is going to be a horizontal shift. Remember that horizontal shifts are kind of opposite from what you would expect. So if you see a minus 1, we normally would think left 1, but this is actually going to go right 1. Since we do not have any vertical shifts or any numbers off to the side here, then that horizontal asymptote is not going to change. So normally the horizontal asymptote is at y equals 0. It's going to continue to be that way for this problem because we don't have any vertical shifts. Okay, so basically we want to kind of prepare for ourselves to have a graph that is an exponential growth graph because our base is 3. And we're just shifting it right 1. So that's kind of what we want to see for our final answer. To get it, make a table. Always make a table if you want to be confident about what points you go through. And a table is always sufficient with x's of -1, 0, and 1. So if we plug in -1 for x, we're going to get a -1 minus 1 or a -2 up in that exponent. And remember, a negative exponent flips you over, so this becomes 1 over 3 to the positive 2, and 3 squared is 9. So the whole thing here is 1/9. If we plug in 0, 0 minus 1 stays -1. 3 to the -1 flips us over and makes it 3 to the positive 1 in the bottom, and that's just going to stay 1/3. If I plug in 1, 1 minus 1 is 0. 3 to the 0 becomes 1. So we have -1 comma a ninth, so that's a really small fraction. 0 comma a third, just a little bit larger, and then 1 comma 1. And remember, we have that horizontal asymptote at 0, so I'm going to draw in that dashed horizontal line. And these are pretty small numbers. If you want more points to plot, you certainly can do so. But because these points are slowly rising up, we're just going to continue that pattern. So there's that growth shape, and then I'm in the left going to skim that horizontal asymptote. So it's a normal exponential growth graph that's been shifted to the right 1. Okay, for the next examples here, we're still going to talk about exponential growth graphs, but what these next 4 examples have in common is they are base E, which is a very common base that you see especially in higher levels of mathematics like calculus. So you want to be familiar with how to work with E. Remember that E is just a special symbol that represents a constant, just like pi is a special symbol that represents 3.14159. E is approximately 2.71828. So it's just a constant that's about 2.7. So to make our graph of e to the x, just like before, we're going to make a table. And in my table, I'm going to use my 3 inputs, -1, 0, and 1. There are no vertical shifts or horizontal shifts or any kind of transformations on this. So if you think about that horizontal asymptote, it's not moving. It's going to stay at y equals 0, and we're going to draw in that little dashed horizontal asymptote so that we don't cross it. Now when we go to evaluate our table, we're going to plug in -1 and get e to the -1. I'll figure out what that is in just a moment. We're also going to plug in 0 and get e to the 0, and we're also going to plug in e and get e to the 1. Now e to the 1 is just the same as e, so this is about that 2.718 number. E to the 0, anything to the 0, is 1, And e to the negative 1 is like 1 over e to the positive 1. So you may not know what that is, but since e is about 2.7 or almost 3, this is going to be roughly about a third. Okay, so this is a small decimal. If you want to get it an actual value, you can use your calculator. And if you notice on my calculator, I have a built-in e button right here, which you can use. You could do 1 divided by and hit second divide to get that e, and you can get that decimal. Or you can use this e to the x button and hit second ln, and this raises e to a power, and we wanted e to the negative 1. So you can do it either way. Hit enter. So this is about 0.367. So it's close to a third. Okay? That's a good value to kind of memorize. It's 1 over e is about 0.3. So now I'm just going to plot these 3 points. Negative 1, 0.3 is right about there. 0, 1 is right about there. And 1, 2.7 would be right about here. Again, we're just approximating. Because this e is a number bigger than 1, it's about 2.7, this should be an exponential growth graph. So we're going to be rising up to the right, and we're going to be skimming the surface of that asymptote on the left. So that's what the graph of e to the x looks like. You should have memorized the size of e, and I would also recommend kind of memorizing or understanding what the size of 1 over e is, about a third, about 0.3. Okay, let's try another example. On this one, we have a plus 2 on the end. So right away, we know that this is going to be a vertical shift up 2, and also very importantly, that's going to shift our horizontal asymptote up 2. So we're going to have a new horizontal asymptote at y equals to this number on the side. So y equals 2. So I'm just going to graph my dashed horizontal line. And it's going to be essentially this graph that we had over here in our last example moved up 2 units. So you can just move these 3 dots up 2 units and you would have the correct graph. If you wanted to start from scratch, you would just make your table and use negative 1, 0, and 1. I'm always using the same 3 inputs for my x for every single one of these problems. So let's plug in negative 1. If I plug in negative 1, e to the negative 1, remember, is the same as about 1/3. So this is going to be approximately 1/3 plus 2, or approximately 2.3. Okay? If I plug in 0, e to the 0 is 1, plus that 2 on the side makes this 3. If I plug in 1, e to the 1 is about 2.7, so when I add 2 onto the side, I get approximately 4.7. So I should be able to do all these without the use of a calculator. So let's plot our 3 points. Negative 1, 2.3, so just a little bit above that asymptote. 0, 3, and 1, 4.7. Exponential growth, because it's that base e, so I'm rising up and to the right, and I'm skimming the surface of the asymptote on the left. Okay, the next example. This time we have a 3 out front. This is another type of transformation, and this is called a vertical stretch by a factor of 3. So all the y values that we would normally get for e to the x are just getting multiplied by 3. So that's just going to make your graph get a little bit steeper faster. So you're going to get a much larger growth at a faster rate. So to get our graph here, when you have this vertical stretch, I haven't shifted my graph up or down at all. I'm just making it grow at a faster rate. So the horizontal asymptote hasn't been shifted at all, so it's still going to be at y equals 0. So let's draw in that dashed horizontal line. And if we make our table of values using our 3 standard x's, negative 1, 0, and 1, let's plug in and see what we get. We're going to do 3 e to the negative 1. Now e to the negative 1, remember, is about a third. So when I multiply that by 3, that's going to be about 1. 3 times a third is approximately 1. Now we're not exactly 1, but we're close enough. If you wanted to get an actual value, then you could just do 3e to the negative 1, and we get about 1.1. So we're pretty close to that. Okay? Let's try 0. 3e to the 0. Well, e to the 0 becomes 1, and 1 times 3 is going to stay 3. If I plug in 1, e to the 1 is about 2.7, and if we multiply that by 3, then we would want 3e to the 1, so it's going to be about 8. Okay, so now we have 3 points to plot. Negative 1, about 1, 0, 3, and 1, approximately 8. So you can see that these dots are getting steeper much faster. It's still exponential growth, but it's just growing quickly. And on the left side here, we're going to skim that horizontal asymptote. So there's my graph. Okay, our last example here with these exponential functions with base e, we have a plus 1, so that plus 1 up in that x, remember, is a horizontal shift, and it's going to be backwards from what you would expect. So a plus 1, normally we think go to the right. This is going to be going to the left 1. We're not shifting up or down at all, just left and right. So because we're not going up or down, the horizontal asymptote stays at y equals 0. So that dashed line is going to stay on that x-axis. To get my graph, let's use our table, negative 1, 0, and 1 for my x's. If I plug in negative 1 plus 1 goes to 0, so e to the 0 gives me back 1. If I plug in 0, 0 plus 1 is 1, and e to the 1 is about 2.7. And if I plug in 1, e to the 1 plus 1 becomes e squared, and e squared is going to be about 7.3, 7.4. So now we have our 3 points to plot. We have negative 1, 1, 0, 2.7, and 1, 7.3. So this is just the normal e to the x graph shifted left 1. And there's my graph. Okay? So whenever you're graphing an exponential function, whatever the base is, it's always sufficient to graph and make a table using x's negative 1, 0, and 1. Plug those in, find out what your y values are, and plot. If you can predict in advance what your horizontal asymptote is and draw that in, that's always a good thing. And your horizontal asymptote will always be 0 unless there's been a vertical shift up or down, and if there has, then it's just going to be the number that's off to the side, like this plus 2 over here. Okay, so sketch in that horizontal asymptote right away, make a table of values using negative 1, 0, and 1, and you'll always get a good exponential graph. Okay? Now to finish off, we're going to do the inverse function of an exponential, which is a logarithm. So we're going to plot some points and get the values of our logs here. Now because logs and exponentials are inverses, we kind of want to think backwards, and we're going to want to make some wise choices for x so that we can simplify this log very easily. So when I decide what I'm going to put in my table for my x's, we're not necessarily going to want to use negative 1, 0, and 1 like we did in the last types of graphs. And for one thing, we don't want to use any negatives because of the log of a negative number does not exist. So what we want to do is keep in mind this base. there are some nice cancellation properties if you think about that base. So for example, if I let x be 1, the base, which in this problem is base 2, and 1 over the base, let's see why those are going to be good choices for my x values. If I use 1, then this is asking for log base 2 of 1. What is that equal to? Well, I'm just going to do a little scratch work here on the side in case you've forgotten how to do logs. This is saying log base 2 of 1. Let's call that y. So to figure out what this is, rewrite this as an exponential. This would be 2 to the y has to equal 1. So 2 raised to what power makes it go to 1? And the answer is 0. We need an exponent of 0 in order for 2 to the 0 to equal 1. So log of 1 is always 0, and that's true no matter what the base happened to be. Alright, so let's try x equals to 2. Then this becomes log base 2 of 2. Well, there's your cancellation property. If your base and this number in your argument here match, then this cancels out and you get 1. And the reason for that is using this same idea that we had before. If we had log base 2 of 2 and we were trying to figure out what it was equal to, we could rewrite this as 2 to the y, and that's supposed to equal to 2. So what exponent do I need here? I need to have an exponent of 1 so that 2 to the first gives me back 2. So log base 2 of 2 is the exponent 1. Okay, let's try one more here. If I do log base 2 of a half, so if I change this to a half right here, we need 2 to the y to equal to a half. What exponent takes 2 and turns it into a 1/2? Well, you need a negative exponent in order to flip it over. So 2 to the negative 1 equals to a half, so this equals negative 1. So all the log values, all these y values here that we're getting for our answers, these are the exponents that you would need to raise 2 to in order to get these numbers over here. Okay? We'll keep practicing that, but for now what we've discovered is by choosing x to be 1, 2, and a half, we got very nice y values, 0, 1, and negative 1, and so now we can just plot these points on my graph and we'll see what our graph looks like. When x is 1, y was 0. When x was 2, y was 1. And when x was a half, y was negative 1. If we try to plug in any negative x's, this is undefined. You're not allowed to take the log of a negative number because you can't raise base 2 to anything and get a negative answer. So these points here should not go past 0. So if I draw my graph, we're going to get something that looks like this. Remember in our exponential functions, when we graphed those, we had horizontal asymptotes? Well, this time, we're going to get vertical asymptotes. So this is going to have a vertical asymptote at x equals to 0. Okay, so let's try that all over again, but this time we're going to do the log base a half of x. So we're going to make a table, and my recommendation for the inputs, the x's that you want to use, are going to be 1, always use x equals to 1, the base, which in this problem is 1/2, and 1 over the base. So 1 over a half becomes 2. And the reason those are going to be nice x's to use is because they're going to give you nice y values to plot. So let's see y again. If I plug in 1, this is saying what exponent do I need to raise 1/2 to in order to get 1? Well, 1/2 to the 0 gives you back this 1. So the answer here is just 0. Log of 1 is always 0, no matter what the base happens to be. Okay, so that's something you want to memorize. If we plug in 1/2 for that x, this is saying what exponent do I need to raise this base of a half to get 1/2 back? Well, I just need to raise it to the first power. So 1/2 to the 1 gives me back a half. So here, another rule to memorize is whenever the base of your log matches this value right here called the argument, these two match, they cancel out, and you always get 1. Okay, and in the last example, we have log base a half of 2. So 1/2 raised to what gives you 2? Well, it needs to be an exponent of -1 to flip it over. So here are my 3 points to plot. 1, 0, 1/2, 1, and 2, -1. So this time the points are going downwards, so they're going to continue to go down, but on the left side here they're going to skim that vertical asymptote. So we have a vertical asymptote at x equals 0. It is not allowed to ever plug in a negative input into a log because that's not defined. So you never want to cross that x-axis. So to generalize, we have the following characteristics. Every log base b of x graph will go through 1, 0, and that's because log of 1 is always 0. If the base is bigger than 1, then you have kind of this growth shape where we rise up and it increases. If the base is a fraction, then you're going to have kind of this decay shape where the graph decreases. This log base b of x graph always has a vertical asymptote at x equals 0, so that was that vertical asymptote, that dashed line. The domain is only positive values. We get close to x equals 0, but we don't actually hit it. So that's why there's a parenthesis here. So the domain is only the positives. The range here is everything, and that's because I continue to go down and up, so I hit all the y values in between. Notice that the domain and range here are exactly the swap of the domain and range that we had for exponential functions. And that's because inverse functions swap domains and ranges. When we go to make our graph, it's always going to be sufficient to plot the following points. When you make a table, this is how you want to set up your table. Always use x is 1, x is the base, whatever the base happens to be, and 1 over whatever that base is. So if you use those 3 x values, then you're always going to get nice y values over here. Okay? So we're just going to practice that a little bit. So if I have log base 6 of x, first thing you want to do in your table is write down the 3 good x's that you want to use. Always use 1. Always use your base, and here the base is 6. And always use 1 over the base, so 1/6. So if I do 1, then this is asking for log base 6 of 1. Remember that log of 1 is always 0. If I plug in 6, log base 6 of 6, remember if these two numbers match, then they cancel out, and this goes to 1. And finally, if I use 1/6, then they don't quite cancel out, but we need to flip over the 6 to make it turn into a 1/6, and the exponent that flips you over is a -1. So this log base 6 of 1/6 gives me -1. So here's my 3 points to plot. 1, 0, 6, 1, and 1/6, -1. Remember, this is going to have a vertical asymptote at x equals 0. That's not going to be shifted here at all because we didn't have any kind of horizontal shifts. So we're going to have that dashed vertical line through the y-axis that we don't want to cross. So we're going to skim that going down, and then on the right we're going to rise up slowly like that. Okay? Let's try the next one here. In the next one, we do have this 2 out front. Remember what that is called. That's called a vertical stretch by a factor of 2. All that does is it takes all your normal y values for log base 1/5 of x and it multiplies them by 2. So it's just going to stretch our graph and make it grow a little bit faster than it would normally. We don't have any shifts going on here, so the vertical asymptote is not going to change. It's going to stay at x equals 0. So let's just go ahead and put in that dashed vertical line. In my table, remember that the x's that you want to always use are 1, your base, and in this problem the base is this 1/5, and 1 over your base, so 1 over 1/5 turns into 5. So if I plug that in, we want 2 log base a fifth of 1. Now remember, log of 1 is always 0, so this is 2 times 0, which is going to stay 0. If I plug in 1/5, remember that log base a fifth, these two numbers match, so this cancels out and you always get 1. 2 times 1 is 2. If I plug in 5, log base a fifth of 5, I need an exponent of -1 to flip 1/5 over to turn it into 5. So this turns into a -1 times that 2, so now we get -2. So here are my 3 points to plot. 1, 0, 1/5, 2, and 5, -2. So here the points are kind of falling, so I'm going to continue that trend. And they're kind of going up towards that vertical asymptote. So it's going to skim that asymptote going up. So there's our kind of decaying shape. Okay? Let's try another one. Log base 3 of x minus 2. Right away, we have a -2 on the side. It's not in parentheses. If it's not in parentheses, then that means it's going to be a vertical shift. And because it's a minus, this means we go down 2. Now, normally in our exponential graphs, that would change our horizontal asymptote. But we aren't using horizontal asymptotes in log graphs. We're using vertical asymptotes. So a vertical asymptote will only be changed, only be moved if you go left or right. So this is not a shift left or right at all. So our vertical asymptote is going to stay at x equals 0. So we will have a shift down, but that doesn't change my asymptote in this problem. So let's sketch in our asymptote, and then let's make our table. The base of my log here is 3. So in my x's, I want to use 1, the base, which is 3, and 1 over the base, which is a third. If we plug in 1, remember that log of 1 is always 0, so 0 minus 2 is going to stay -2. Okay, so now if we plug in 3, we're going to have log base 3 of 3 minus 2. Remember that if these two numbers match, they cancel out and the whole log goes to 1. So this is going to be 1 minus 2, which is -1. And finally, if I plug in a third, log base 3 of a third, I need an exponent of -1 to flip over the 3. So log base 3 of a third reduces to -1 minus that 2 on the side, so we get a -3. So the 3 points that I'm going to plot are 1, -2, 3, -1, and 1/3, -3. So we have this graph that's rising up towards the right slowly, and it's going closer and closer to that x-axis on the left. Okay? The next few examples are going to be more log graphs. However, this time they are ln graphs. Remember, an ln is a natural logarithm, and it means log base e of x. And we normally don't write that base e in there, we just write it as ln. So whenever you see ln, it's always an implied base e. So in this first example, let's just graph what a normal ln of x graph is going to look like. So we're going to do that with our table. Remember that in your table you want to pick x's that are 1, your base, and this time what's the base of an ln? Remember, I said this was a base e, so this is going to be e, and then we want 1 over that base, so 1 over e. So now if we plug these in, this is going to be ln of 1. If it helps you, if you're not that familiar with logs, change this to log base e of 1. Remember, log of 1 is always 0 no matter what base you have. If we want e, and plugging in e, ln of e is like log base e of e, so even though I don't have it written over here, the base here does match the e, so these are going to cancel out and give me that 1. So ln of e is just 1. And ln of 1 over e is like log base e of 1 over e, and again we need that -1 exponent to flip e over into 1 over e. So logs are always the exponent that you need. So here's my 3 y values. Let's plot our points. 1, 0, it's right there. E, 1. Now what's the size of e? Remember e was that 2.7. What's the size of 1 over e? Well, e is about almost 3, so this is about 1/3. So that's the kind of values you want to use when you're plotting your points. So if I want e, 1, then it's going to be about 2.7 for x, 1 for y. So go over 2.7 and up 1. And then for the last table value here, we want 1 over e, -1, so that's going to be about 1/3, -1. This was not a shift left or right at all, so my vertical asymptote stays at x equals 0. And I'm going to go and skim the surface of that asymptote and then rise up slowly to the right. And there's my graph. Okay, let's try a couple more of these. Here we have ln of x minus 3. There's no parentheses here, so this minus 3 is off to the side. This is going to be a vertical shift down 3. Remember, for log graphs, that does not affect your asymptote. If this was an exponential graph, it would affect your horizontal asymptote, but it does not affect our vertical asymptote. So the vertical asymptote for this will stay at 0. So to get our graph, we're just going to take the graph of ln and move it down 3, or you can use a table. And remember, in your table, because this is an ln, the base is e, so we want to use 1, e, 1 over e. So 1, the base, and 1 over the base. Those are your 3 inputs. So if we plug in 1, ln of 1, or log of 1, goes to 0. So this is going to be 0 minus 3, or -3. If I plug in e, ln of e, remember, is log base e of e. And since the e's here match, this goes to 1, and 1 minus 3 is -2. And finally, if I plug in 1 over e, that's log base e of 1 over e. So I need an exponent of -1 to flip it over. So this is going to be -1 minus 3, which is -4. So my 3 points to plot, 1, -3. E, which is about 2.7, -2. So go over 2.7, down 2. And then 1 over e, which is about 1/3, -4. So go over about 1/3, down 4. So there's my 3 points. It's rising to the right, and it's going to skim that asymptote on the left. So there's my graph. Okay, one last example. This time we have this minus on the outside. Remember, when it's on the outside of your function, not next to the x, but outside of the function, then it's a reflection over the x-axis. So that's just going to flip our ln graph, which normally looks like this, and it's just going to flip it upside down. So now it's going to look like this instead. So let's get a few table values here so we can plot this for sure. My base for my ln is e, so for my table values I want to use 1, e, and 1 over e. If we plug in 1, ln of 1 is a log, so log of 1 is always 0, and that minus isn't going to affect your 0. If we plug in e, ln of e means log base e of e. Since these e's match, this cancels out to 1, but we had that minus in front, so now this is going to be negative 1. And then for the last value here, we want ln of 1 over e. There's that minus in front, and this is log base e of 1 over e. We need e to the negative 1 to flip over to 1 over e, so this reduces to a negative 1, but there was that minus in front, so negative 1 becomes positive 1. Our vertical asymptote does not change because we didn't have any shift left or right, so this is going to stay at 0. So my points, when I plot them, are going to be 1, 0, e, which is about 2.7, comma negative 1, so go over 2.7, down 1, and 1 over e, which is about a third, comma 1, so go over a third, up 1, and now I'm going to get these points going up towards that asymptote on the left and decreasing to the right. And my graph is a little bit crooked here, but you get the idea. So it's that same ln graph but shifted upside down. Okay, let me clean that up just a little bit. Alright, so in summary, here's what we found. For exponential functions, you can always get a nice exponential function graph by using the x values negative 1, 0, and 1, and finding what those y values are. If the base b is bigger than 1, you'll get this growth shape, and if the base b is a fraction, you'll get this decay shape. And remember, these always have horizontal asymptotes starting at y equals 0. That may change if you have a vertical shift up or down. For logarithmic graphs, you want to make a table, and your x values that you want to use should always be 1, the base b, and 1 over the base. If the b is bigger than 1, you get this growth shape. If the base b is a fraction, you get this decay shape. And this time we have vertical asymptotes at x equals 0, and that will only change if you have a horizontal shift left or right. Alright, that concludes our lecture on graphing exponential and logarithmic functions. Good luck.